Hello, chemistry students. So we continue with our gas unit and atmospheric chemistry by looking at our last gas law, the ideal gas law. Now, there's a formula, but we'll get into that in more detail in just a moment. Okay, but before we look at this formula, let's start with what an ideal gas is. These are a few assumptions that need to be made. There are a few more points to add to this, but I'm not going to go over those. These, I think, are the main ones, the most important ones for us to look at right now. So the first point is that an ideal gas is only, the amount of energy is only dependent on the kinetic energy it has, which just means that temperature increasing or decreasing, so temperature increasing or decreasing will affect its velocity, its movements, its rate of collisions, right? So talking about that, as atoms collide with each other, an ideal gas has to also be elastic, completely elastic, which means when they collide with each other, they don't pick up energy, they don't gain energy, and they also do not lose energy. Also, atoms of gas do not interact with each other, so they can't react with each other. Now, we know this isn't, of course, entirely true, but to meet these assumptions, we're making this point. Also, it will not leave its gaseous stage, so it will not condense into a liquid. Now, of course, no gas fits these definitions or these assumptions perfectly, but they are fair assumptions to be made and ones that are required when we're working with the ideal gas law and to simplify calculations. Okay, so here it is. PV equals nRT. So P stands for pressure, V stands for volume, M, as you've seen before, stands for moles, R is something new, that's our gas constant. We'll get into those details in just a bit, and T is for temperature in Kelvin. So here we are. So pressure has to be in kilopascals, volume in liters. Temperature, like I said, not in degrees Celsius or Fahrenheit, it's in Kelvin, although there are versions of this ideal gas law that use Fahrenheit or Celsius, but we're going to stick with Kelvin. And of course, N is moles. Now that gas constant is this, it's 8.31, and it's a constant. If you're taking physics, you know that there are many physical constants, universal constants that are used, and this is just another one of them. So 8.31, here are our units. K, I like to remember this as kPa over kmol. So kilopascal liters over Kelvin moles. Okay. So, just a reminder that an ideal gas at STP will occupy, so 1 mole of it will occupy 22.4 liters. Now, having said that, we can derive where our gas constant comes from by looking at how the ideal gas law was developed. So at STP, and considering just 1 mole, and therefore with a volume of 22.4 liters, you can plug all of these values in, and you see that it would have given you, or it gives you constant R. Now this R value can be isolated, so we isolate for R, and we get 8.31 kilopascal liters over Kelvin mole. Okay, now this isn't something that you'll need to do on any kind of evaluation, but just so you know where this comes from, this isn't some just made up number, this is how it was developed. Okay, so again, reminder, PV equals nRT, as we begin then our couple of sample problems. Okay, so first one, how many moles of H2 is in a 3.1 liter sample of hydrogen gas measured at 300 kilopascals and at 20 degrees Celsius. So it helps to write down what you're given. So pressure is 300 kilopascals. Right, then you are also given volume 3.1 liters. Temperature is given to you in 20 degrees Celsius. We have to convert Celsius to Kelvin, so you add 273, and we get 293 Kelvin. Yes. Right, we're going to use the ideal gas law. If you're writing a quiz or a test or a worksheet with mixed questions, a good way to figure out which law to use is to simply write down what you're given. PV, temperature, then you're being asked for moles. We should write that down. We don't know what moles is. So because you're giving all of these variables, all of these measurements, and we're being asked for moles, it's indicating we're going to use the ideal gas law. So you can plug numbers in now, and then isolate for your unknown, or you can just isolate for N, and we get PV divided by RT. plug in your given values, and we get 300 kilopascals, 3.1 liters, 8.31 kPa, kilopascal liters over Kelvin mole, and our temperature is 293 Kelvin. Now watch how units cancel out. Kilopascal, kilopascal cancels out, liters, liters cancels out, Kelvin, Kelvin cancels out, and you're left with the unit you're looking for, and your answer is 0.38. Okay, so there you go, 0.38 moles. Next, how many grams of O2 are in 3.15 milliliters, right? So this has to be converted to liters, and it's asking us for grams. Grams. Okay, before we continue reading, you know that you can get to grams if you have moles, and we've learned to do this a few units back. Right, so in a container that has a pressure of 12 atmospheres, right? So this also has to be converted, so a little bit more work to do in the first one. This has to be converted to kilopascals, and look, 25 degrees Celsius has to be converted to Kelvin. Okay, so we're going to jump into these conversions right away. Pressure, 1 atmosphere, 1.1, it's 1 or 1.3 kilopascals for every 1 atmosphere, so that conversion is just multiply this by 1.3, and we get pressure at 1,215.9 kilopascals. Okay, volume given to us is 315 milliliters, which we can convert by dividing by 1,000 to 0.315 liters. Temperature, you just add 273 to it, and you get a temperature reading or temperature measurement of 298 Kelvin. Good. Now do what we did before. Solve for N as PV is equal to RT, and we get pressure at 1,215.9 kilopascals, volume 0.315 liters, and then your gas constants. Oh, it's not letting me write this. Oh, I have to write it here. K mole. Okay. 298 Kelvin. Okay, again, units cancel out. Kilopascal, kilopascal, liters, Kelvin, and we're left with moles at 0.1547 moles. Now, we finally have moles, and we can convert this now to grams. Now, if you forgot the formula, that's okay, probably best, let's just use the factory method. Okay, so we need grams, we have moles, we're going to multiply that by a conversion factor that has moles at the bottom and grams at the top, so grams per mole. Now that of course refers to the molar mass, and we're talking about oxygen here, so the molar mass, looking at the periodic table of O2 gas, is 32 grams per mole. So notice how mole cancel out, and we're left with a final answer at 4.95 grams. And that's it. Okay, so the next stage of this, of course, now that we can figure out moles of a gas, is stoichiometry. So stay tuned for that lesson we'll post that later today. In the meantime, there's a homework package posted online. It's called actually Ideal Gas Law, and there are extra sheets as well. Extra practice for you. Ideal Gas Law is what that worksheet is called. Post any questions. I have also, normally if we were in class, there's some work to do that we would take up together or circulate through. So these are all good questions to be asked or for you to practice, and answers are also included within the PowerPoint posted online. So I hope this helps.